Okay, so think back to the early days of the COVID-19 pandemic. Remember how we were just flooded with all these different forecasts and models? And they all seemed to tell a totally different story. It was confusing, right? So why was it so darn hard to predict? Well, we're going to dive into that today by looking at this really fascinating research paper from Nature Computational Science. It lays out a new approach using a special kind of AI, one that doesn't just look at the data, but actually understands the fundamental rules of how a pandemic spreads.
All right, so here's the game plan for this explainer. First, we'll tackle that core prediction problem. Then we'll look at all the different types of models out there. After that, we dive into the cool stuff, the physics-informed AI. We'll unpack a super important concept called identifiability, see how this all performed on real-world data, and wrap up by looking at what this all means for the future of modeling.
Okay, let's jump right into part one, the prediction problem. And to really get a feel for this challenge, you gotta put yourself back in the mindset of those early pandemic days. Total chaos, things changing by the hour, and researchers just scrambling to make sense of it all. So this was the million-dollar question, right? Why were all these predictions so different? You'd see these reports from super credible teams at top universities all looking at pretty much the same data, but their forecasts would be worlds apart. It created this thick fog of uncertainty, not just for us, but for the people who had to make massive decisions based on this stuff. And the authors of this paper, they just nail it. They say the problem wasn't that the models were bad. It boiled down to two huge issues. First, the data itself was messy, noisy, and just plain incomplete. And second, there's this really tricky concept called identifiability. Think of it like this. Imagine two totally different recipes somehow produce the exact same cake. Identifiability is the question of, can we be absolutely sure we have the one true recipe for this pandemic, or could a bunch of different combinations of factors be fooling us into thinking we do? So what do you do when you're faced with that kind of deep uncertainty? Well, the researchers' answer was kind of brilliant. Instead of hunting for one single perfect model, they decided to embrace variety. Which brings us to part two, a plurality of models.
So, get this. They didn't just test one or two ideas. They analyzed 9 different models across 3 major categories. First, you've got your integer order models. These are the classics, the standard approach, thinking about the pandemic in simple, fixed-rate steps. Then you have time delay models. These add a crucial layer of realism by accounting for stuff we know exists, like the lag time between getting infected and actually showing symptoms. And finally, there are the fractional order models. Now, these are a whole different beast. They're built to capture this complex idea that the past has this lingering, fading influence on the future, what the paper calls memory effects. It's like the difference between a simple, clean echo and a really complex one that decays in a very specific, nuanced way. And this right here is a really crucial mindset shift. This project wasn't some kind of model deathmatch to find the one true winner. Nope. The goal was to build a really robust framework, a system that could screen a whole bunch of different models, compare them, and figure out which ones are the best candidates for the job, for a specific set of data at a specific point in time. Okay, but how do you actually test all these different and complex models? Well, you're going to need a seriously powerful tool. And that brings us to the real heart of this research in Section 3, a cutting-edge kind of AI. It's called a physics-informed neural network, or PIN for short. So, what on earth is a PIN? Well, think of it as a deep learning framework with a really cool twist. It doesn't just learn patterns from data like a normal AI. It's constrained to obey the fundamental mathematical rules of the system it's studying. In this case, the physics of how a disease actually spreads.
And I love this analogy for it. A traditional AI is like a student who just crams for a test by memorizing old exams. They might get the answers right, but they don't really get it. A PIN, on the other hand, is like a student who also studies the textbook and learns the fundamental principles. Because it's trained on both the data and the rules, its answers are just way more robust and trustworthy.
Okay, this diagram might look a little intense at first, but it really shows the magic behind how a PIN learns. Zero in on that loss box at the bottom. You can think of that as the AI's final grade. Now, to get an A+, the network has to do 2 things really, really well at the same time. On one hand, it has to make sure its predictions match the real-world data we give it, but on the other hand, it's also being graded on how well it follows the mathematical rules of the model, what you see here as ODE residuals. It basically gets penalized for breaking the laws of physics. It has to ace both parts of the test, no cheating allowed. And these guys didn't stop there. Remember those super complex fractional order models we talked about? Well, the math behind them is pretty gnarly. So the team actually built an upgraded version, something they call an F-pin, or a fractional pin. This basically let them apply the same powerful physics-based approach to even the most complex models, the ones with those deep memory effects.
All right, let's move on to section 4. This is all about a crucial quality check you have to do to make sure a model is actually trustworthy. And we're going right back to that key concept from the beginning, identifiability.
So it turns out identifiability comes in two flavors. First, you've got structural identifiability. This is purely theoretical. It's like looking at the blueprint for a car and asking, is this design even possible? Does it make sense on paper? Then you've got practical identifiability, and this is the real-world road test. It's like asking, okay, we built the car, but when we drive it on a bumpy, potholed road, do the wheels stay on? In other words, when you feed the model messy, noisy, real-world data, do its answers stay stable, or do they just fly all over the place? And this chart is just a fantastic illustration of that practical road test. Check out the graphs on top. They're tracking key things, like the transmission rate over time. See those colored bands? That's what happens when you intentionally add noise to the data to simulate real-world messiness. The key thing to notice is how tight those bands are. The model's answers don't wobble all over the place. They stay stable. And then look at the bar charts at the bottom. That's the error rate. And again, the error stays super low. This is the proof. This tells you the model is robust, it's trustworthy, it's practically identifiable. Okay, so now for the moment of truth. Let's see how this whole thing actually performs in the real world. Section 5 is where we see this entire framework, all the models, the pins, the identifiability checks, put to the ultimate test against actual COVID-19 data. And the team followed this super rigorous 5-step process for everything. Step 1, you clean up the data. Obvious, but important. Step 2, you run those critical identifiability checks to make sure your model is sound. Step 3 is where the pins get to work, figuring out not just the known parameters, but also inferring all the hidden dynamics of the pandemic. And only after all of that do they get to step 4, forecasting, and step 5, which is just as crucial, quantifying exactly how uncertain those predictions are. And to really put this thing through its paces, they didn't just test it on one city. They threw a whole bunch of diverse data sets at it to see if it would hold up. We're talking about a massive dense city like New York, different states like Michigan and Rhode Island, and even an entire country, Italy.
And just look at these results for New York City. Each of those lines you see is a key parameter of the pandemic, like the transmission rate. The really amazing thing here is that they aren't flat lines. The pin is figuring out how these values changed over time, day by day. This is absolutely huge. It means the model isn't static. It can actually see and adapt to real-world changes like lockdowns or when a new variant popped up and changed the rules of the game. So here's the bottom line, the most important takeaway. This system does two incredible things at once. First, it perfectly fits the data we can actually see, like daily case counts. But second, and this is the game changer, because it's forced to obey the laws of physics, it can intelligently figure out the stuff we can't see. It can give us a robust estimate of hidden things, like the true number of asymptomatic people out there at any given moment. It's like it has X-ray vision.
So all of this brings us to the big picture, our final section. What does this incredibly powerful new approach mean for the future? And I'm not just talking about pandemics, but for all of scientific modeling.
Look, if there's one single thing you walk away with today, let it be this. The future of modeling isn't about finding one single perfect crystal ball. That's a fool's errand. The future is about having robust, flexible frameworks like this one. Toolkits that let us test lots of different ideas, really understand their unique strengths and weaknesses, and most importantly, be upfront and honest about how uncertain our predictions really are. And maybe the coolest part of all, really showing the true spirit of science, is that the researchers didn't lock this away. They packaged up the entire framework into a public, open-source Python library. It's called PinCovid, and it's up on GitHub right now for any researcher anywhere in the world to download, to use, and to build on top of. It's a tool for everyone. Because honestly, this amazing work on pandemics is really just scratching the surface. It leaves us with a much, much bigger and, frankly, more exciting question to think about. What happens to scientific discovery in every field, from climate science to building new materials, when our AI tools don't just see patterns in data, but actually start to understand the fundamental laws of the universe?